All right, so we want to take a look at questions involving a particle placed inside of a smooth hollow ring. So we are going to be looking at two particular examples, and we are taking these questions from the textbook, the Further Mathematics course book. So we're starting with this question here, and it says, a particle P of mass m is at rest on the lowest part of a semicircular piece of metal. The semicircle has radius a and is completely smooth. The particle is projected with a horizontal speed of root 8 GA. So on part A, find the speed of the particle when it is just about to lose contact with the semicircle. All right, so we have a very nice question here, and we want to see how we can answer it. Now, um, what we're going to do is we're going to take a general point, okay? I'll take the particle to be along its motion to be at some general point, which is this point here. So I'm just going to have it like this, all right? And for this general point, let's say the angle, okay? The angle it makes with the vertical, okay? If we are going to draw a radius from the particle to O, let's just call that angle alpha. All right. Let's also say at this general point, the particle will be moving at a speed, okay? And let's call that speed v. All right. So what I'm just going to do is I'm going to take this v, this speed v. Let me just place it on here. And it is going to be tangential, okay? Tangential to the circular path. So this is what we have. And we are also going to consider that the weight of the particle, which always acts vertically downwards, should be mg. And since there's contact, we also expect there to be a normal reaction. So there's a normal reaction force. So that's the normal reaction here, directed towards the center. So we have R right here. Okay. So for this general point, we are going to consider, firstly, Newton's second law. And for Newton's second law, we're going to say here that the resultant force of the forces acting at this particle when it is at the general point is going to be R minus the component of mg. Okay, let's have the component of mg, which is this component here. All right, so we have a right angle here. So this component of mg, which is technically mg cos alpha, because the angle here is alpha. So it's actually mg cos alpha, okay? So that's the resultant force. Actually, the centripetal force, the resultant of the normal reaction, and the component of mg. This has to be equal to mass times acceleration, which is mv squared over the radius. In this case, that's a. So we're going to have this equation as being equation 1. Let's also consider the principle of conservation of energy. And when we talk of the conservation of energy, we are saying that initial energy is equal to final energy, basically. So let me write that down. Initial energy, which is the energy when the particle was initially projected, is equal to final energy. And final energy is the energy of the particle at the general point, okay? So basically, the initial energy, we hear that the particle was projected horizontally, okay? Here they say the particle is projected with a horizontal speed of root 8 GA, right? So we're going to say the initial kinetic energy is going to be half m and v squared, which is just going to be 8 GA, and that's going to be plus the gravitational potential energy. If we take this level to be h equals to 0, this whole level to be h equals to 0, that means that the gravitational potential energy at this point is going to be minus mga. So we will have here minus mga, and this is equal to the final energy, which is the energy of the particle at the general point, the speed is v. So the kinetic energy is going to be half mv squared, and that's going to be plus the gravitational potential energy, which in this particular case, from h equals to 0, this is going to be a cos alpha. So that's minus a cos alpha, basically. So we're going to have minus mg a cos alpha. All right. So with what we have right here, we can simplify. So we basically here have 4 mga minus mga, and that's equal to half mv squared minus mga of cos alpha. All right, so that's 3 mga is equal to half mv squared, and that's minus mga cos alpha. Now, from here, I'm going to multiply both sides by 2 over a. And if we do, we will be having here 6 mg being equal to mv squared over a minus 2 mg of cos alpha. All right. So we are saying that mv squared over a is equal to 6 mg plus 2 mg cos alpha. So this is what we have right here. All right. Now, the question is saying we should find the speed of the particle when it is just about to lose contact with the semicircle. So we know that it will lose contact with the semicircle right at this point. All right. And at this point, the value of the angle alpha will actually be equal to 180 degrees, because alpha is the angle that the radius drawn from the particle moving in the circular path makes with the downward vertical. So when it is at this particular point, alpha will have a value of 180 degrees. So I'll say here, when the particle loses contact with the metal ring, alpha will have a value of 180 degrees, right? So therefore, we will be having mv squared over a being equal to 6 mg plus 2 mg, and cos of 180 degrees is actually minus 1. All right. So we have mv squared over a is equal to 4 mg. And if we multiply both sides by a over m, then we'll be having here, these will cancel. So that'll be v squared is equal to, this is going to be 4ga. All right. So to get the value of v, we'll do the square root of 4ga. So v is actually 2 root of ga. So that's how we find the speed of the particle when it is just about to lose contact with the metal ring. All right, let's go on to the next part. The next part of the question says, the particle then travels as a projectile until it hits the ground. Find the horizontal distance between O and the point where the particle hits the ground. Okay, so when it loses contact, they say that it will move like a projectile. So it is going to be projected, in this case, tangential to the circular path, which in this case will be horizontally. And the speed of projection is the speed with which it which it had when it lost contact with the metal. So this particular speed. So that's 2 root ga. So we have 2 root ga here as the speed of the particle. That's actually now the speed of projection. All right. So the particle is going to move, okay, follow something like this as its trajectory. All right. And at this particular point, it will have coordinates, all right? An x coordinate and a y coordinate, right? So we are going to make use of the equation of trajectory for that. Okay, let's go to part B. So we're saying the equation of trajectory is y is equal to x tan theta minus gx squared over 2u squared of 1 plus tan squared theta. Now, the question says we should find the horizontal distance, all right? That's what they say here. The horizontal distance between O and the point where the particle is the ground. So the horizontal distance is actually this distance. That's actually what we're looking for, which in our case is x. It's an x value. So we are actually looking for x, all right? Um, do we know what y is? We do know what y is. Y is the vertical distance vertically downwards. So this whole distance is y, okay? And it's below or this point, the top point. So it's going to be the radius here is a, below it's a. So it's minus 2a basically for where our reference point is that top point. So y is minus 2a. All right. Um, this particle was projected horizontally, so there is no angle of projection. So theta is 0. And what else do we want? From what's been given, we know that the initial speed of projection is 2 root GA. So the speed of projection U is the square root, actually is 2 root GA. And we can say that U squared is 4GA. All right. So if we plug these values into the equation of trajectory, we'll be having minus 2a for y is equal to x tan theta. Tan 0 is 0. So this part will become a 0. And that's going to be minus gx squared. So gx squared. And that's over 2u squared. That's 2 of 4GA. And that's of 1 plus tan squared theta. Tan of 0 is 0. So that's just going to be 1, right? So 2 times 4 is 8 here. Multiply both sides by 8GA. We will get minus 16a squared g, and that's equal to minus gx squared. Remember, we're looking for x, the horizontal distance. So x squared is equal to 16a squared. Square root that. So x comes out as 4a. So this here is the value of x, and that's the horizontal distance from O to the point where the particle is the ground. So that's how we answer this particular question. All right, so we want to move on to another example. So we have a question here, and it says, a particle is held at rest on a smooth circular track, which is an arc of radius a. The track is standing in a vertical plane, and it is fixed to a horizontal surface. The points O and A are such that OA is horizontal, as shown in the diagram. The particle is released from rest and proceeds to slide down the track. So on part A, find the speed of the particle at the point where it is just about to lose contact with the track. All right. So we want to answer that first part. All right. So for this particular question, we are going to consider the particle when it is at this particular point, because that's the point where it is just about to lose contact with the track. All right. So at that point, we can apply Newton's second law. All right. To say that, okay, the forces at play here will be the weight. Okay, let me just draw that properly. The weight, which will be acting vertically downwards, and it's mg, the normal reaction force. Okay, let me draw it well. So the normal reaction force, and that's going to be R. Then we have a downward vertical here. So that's the downward vertical, where we're saying that the angle here should actually be 45 degrees, right? All right. So that's what we have. And I think that's much of what we need. All right. The components of mg, okay, let me draw them. So this is a component and this is another component. All right. So for Newton's second law, the centripetal force is the resultant of R and the component of mg, which is mg cos 45, okay, cos 45 degrees, okay. And this has to be equal to mass times acceleration, which is m of the speed. We don't know what the speed of the particle is here. So I'll just say the speed is v. So it's m v squared over a. So that's our first consideration. All right. I'll just call this one. So let's look at the conservation of energy. All right. So initial energy, okay, which is the energy at A should be equal to the total energy when the particle is about to lose contact with the track. Let me just call that, well, I'll just call that point P. So energy at P. All right. So we're saying that energy at A, where the particle was projected, it was projected vertically downwards, but we've been told that the particle was released from rest. So the initial kinetic energy is 0. Then when it comes to the gravitational potential energy, I'm just going to take this level to be H equal to 0. So the GPE is also 0. So we're starting with 0 energy. And at P, the kinetic energy will be half m v squared, right? V at P. And that's going to be plus, actually, that's going to be minus mg a cos of 45 degrees, okay, because the vertical distance from h equal to 0 is a cos 45 degrees, so that should be right, okay? So we're going to say that that's going to be half mv squared is equal to mga of cos 45 is root 2 over 2. Multiply both sides by, let's multiply both sides by 2 over m. So this side by 2 over m by 2 over m. And if we do so, these will cancel, all right? And we are left with v squared. And here we are left with root 2 of ga, all right? So square rooting both sides, we get the square root of root 2 ga. All right. So that's what we will be having for our answer here. Okay, that's the speed. All right. The speed of the particle at the point where it is just about to lose contact with the track. Let's go on to part B. Part B says, find the greatest reaction force on the particle when it is in contact with the track. All right, so the greatest reaction force will happen when the particle is at the lowest point. So when the particle is here, all right, when the particle is at this point, that's where the greatest reaction force will be. So the weight will be acting vertically downwards, and that's the weight is mg, right? Okay, and we also have the reaction force, which is the maximum reaction, that's R. All right, so if we use Newton's second law here, we will be saying that R minus mg, okay, so let's do that. So on part B, R minus mg should be equal to the speed, okay, when it is at the bottommost point. So the speed, let's just call this position B. So at B, the speed will be actually we have m of VB squared over the radius, which is A. All right, so this is what we have. So I've applied Newton's second law. Now, applying the conservation of energy, this was Newton's second law. Applying the conservation of energy, we'll say that initial energy at A, which is actually zero, okay, so energy at A is equal to energy at the point B. So we had said it's zero at the beginning, but at B, the kinetic energy will be half m of VB squared, and that's going to be minus mga. If you take a look at it, it's minus mga. That's the GPE at B. All right. So with what we have, we can find VB squared, right? So we're saying that a half m VB squared is equal to mga, multiply both sides by 2 over m, and we'll be having on the left side VB squared is equal to 2GA. So if we substitute that into this equation, we'll therefore be having R minus mg being equal to m of VB squared, but VB squared is 2GA. So it will be 2, or let me just say m of 2GA over A. All right. So we know that these will cancel and we're left with 2mg. So R minus mg is equal to 2mg. So R will come out as 3mg. And this is the answer. That's the maximum reaction force as required by the question, the greatest reaction force of the particle on the particle. So that's 3mg. And that's basically how we would answer such a question.